one of the more complex examples that we see in this class, because anytime you get into differential equations and Laplace and all that type of stuff, right, the math can be a little bit messy. But, we saw problems like this in ELC251-06 when we talked about the transient response for first order and second order networks. Now we're also going to see it in this class when we look at the transient response of the Miller integrator. You saw a lot of it, or at least the mathematical basis behind it in ELC272. So the repetition here, hopefully, each time will make you a little bit more familiar and comfortable doing this type of process. Okay, so consider a Miller integrator. Find the response of the Miller integrator to an input pulse with a 1 volt height and a 1 millisecond width with these values that are given. Okay, so first we start off by looking at the case where we don't have any feedback resistance in parallel with the cap. So for that one, the solution is relatively easy. We know that the output will just be the integral of the input. And I'm not even going to look at the math, okay? I'm just going to go ahead and talk about this conceptually. So what does the pulse look like? The pulse, they said, has a width of 1 millisecond. So this is the input that's being supplied. It'll go up to 1 volt, and then it'll go back down to 0. We know that the Miller integrator has a negative coefficient, so it makes sense that the output is going downward as opposed to upward. And it also makes sense that this is a straight line with a constant slope. Because what is the integral of a constant value? It's a line with a constant slope, right? Where the value of the line determines what the slope is. So that's what we have here. We have a pulse where it goes up to 1, then goes back down to 0. While the pulse is high, the integral of it will be a line with a negative slope. And then, once it returns to 0, what's the integral of 0? Simply just a flat line. So the shape of this response makes sense given the input that is provided. Now we can look at the math a little bit. So first things first, why do I split it up into two different pieces? And it's really important that I ask a lot of questions in this example, because if I don't ask a lot of questions and I don't get your participation in this, when we're talking about the weighted summer, I can kind of just explain it and you can just absorb it. But for this example, if I don't ask questions and get input from you guys, it's going to be like a train just flying past you. So why do I have to split this integral up into two different pieces? Yes?
Well, because the pulse is kind of two different parts also.
Exactly. Piecewise. Exactly the term I'm looking for. So because the input is piecewise, we take the integral in two different pieces. So what we have is the integral from 0 to 1 millisecond, and then we have the integral from 1 millisecond on. So from 0 to 1 millisecond, what does the integral look like? It's negative 1 over RC, as dictated by the slide two, 3 slides back, times the integral of 1 plus whatever our initial value is. So we're assuming that we're starting out at 0. And so what we end up with is a line that's going downward with a slope of negative 1 over RC, right? Because the integral of the 1 will simply be t. So you end up with negative 10,000 t. And what that means is at 1 millisecond, if we plug in 1 millisecond right here, we end up with negative 10. So it'll go from 0 to negative 10 volts over that 1 millisecond. All right. Now let's look at the second piece. So on the second piece, negative 1 over RC times the integral of 0. What's the integral of 0, right? The integral of 0 is going to give us a 0. We're going to be left with the initial condition. You cannot forget about the initial condition. So these are two different initial conditions because they're different windows in time. The initial condition for the first window is 0. The initial condition for the second window is the final value of the first window, right? They're back to back. So what this is saying is that this part will go away, and here we'll be left with the integral plugged in with the 1 millisecond point in time, which essentially, again, just the -10, and that goes on forever because we don't have any leakage. We don't have any path for that charge to be lost. So you can follow the 3 steps of the integral. It's perhaps a little bit, I tried to do it in the most complete way possible, but really the second line in each one of these is a little bit more complicated than it needs to be. We know that it's just going to be whatever the output is staying at that value. Okay? Yes?
So under the V out of 1 millisecond, it says the negative RC. Is that talking about the negative RC like that's right like previously?
Yeah, same one. Yeah. Mm-hmm. Essentially, it's just taking this value, pushing it down here, and plugging in 1 millisecond.
Okay.
That's all that it's doing. Because you can see what you end up with is, so the top is -10,000 t, the bottom is a definite integral. -10,000 t plugging in 1 millisecond. Minus, I mean, you minus the 0, but the 0 is going to be 0. Okay. So now, the part that we're going to do on the iPad. Second part is where we do have this parallel resistor. So I'm going to show this slide, and then we're going to jump into the details of doing the math. But this slide actually does give a very good description of what's going on, at least to start us off. So this is what the original configuration of the Miller integrator with the parallel resistor looks like. Okay? This is what it looks like with the amplifier removed. Again, we're assuming ideal characteristics of the op-amp. That means that we have a virtual short that applies right here. So the voltage at the intersection between this, this, and this is 0 volts, same as the ground. We also know that no current can flow into the amplifier. It has a 0 bias current. And so therefore, we can actually get rid of the amplifier altogether. And so this is a simplified, redrawn configuration of what we have above. All the important parts that we need in order to solve for the transient response. We have the resistance, series input resistance, as well as the feedback capacitance and the feedback resistance. So these are our input. This point is the same as this point right here. And then our output is our output. And then now you can see as we start off the problem, how are we going to define it as this first order differential equation. And this is what we have to solve in order to get where we need to go. All right. So give me a second to get the iPad loaded up. Now, I think the question a lot of you will ask is, well, should I expect to see something like this on the exam? The answer is yes and no. I think that this type of problem would be relatively impractical to ask on an exam in its full form because I don't like to ask questions that require, an hour's worth or, 30 minutes worth of math. However, that being said, there's a lot of ways that I can make this problem easier. Taking out certain values, making certain assumptions, asking you to only, calculate part of it. Let's say instead of finding the response, calculate the transfer function in the Laplace domain. There's lots of ways that I could just give you part of this. So I do think this is an important problem to spend time on. Not only just for this class, but also, one important thing to come out of this class with the combination of ENG212, 251, and 272 is knowing how to deal with these transient response problems. Give me 1 second here. All right, so what I'm going to do is I'm going to actually leave the slides up on the left-hand side, and we'll use the iPad on the right-hand side so you can compare and contrast. Yes?
Why are the IRC negative?
Why are they defined in the directions that they are? Is that what your question?
Why are they negative instead of kind of going on? I don't know. Yeah, why are they negative?
So we define those. We set those up as part of our problem. So we could set them any way that we wanted to. We could flip them and then they would be positive. It's just a judgment call. So really it's arbitrary.
Is it just because they're going from the 0 volts to VL?
You know what? We're going to go through and derive this expression right now, so I think that'll answer your question. So let's go ahead now and jump into this. Okay, so example 2.5, solve for the transient response of the circuit below. Now I'm not going to draw the original amplifier. I'm just going to go ahead and draw the simplified version that we just showed. And so that has our V in, our resistance, then we have our capacitance, we also have the parallel resistance. So this is called R1, this is called CF, and this is called RF. Now let's label all of the voltages and currents that we're going to be dealing with in this circuit very clearly. So what I'm going to do is I'm going to call this VR1, and I want the passive sign convention to obey this. So I'm going to define this as I in. In reality, I don't need this value right here because this is 0 volts. So this is the same as V in. So I don't need to give it a separate name. Then what we have, and sorry, this is not ground. I misdrew this. This is actually V out. All right. So our V out has a polarity that looks like this, going negative positive, right, because our V out is actually at the bottom of the circuit. And I think this is the reason why your question about the negatives comes in, because we decided to still draw the current directions in this way, IC and I are, which you'll see they violate the passive sign convention. So that's the reason why they end up being negative. So I think that's all the important stuff that I have to label here. The other thing that I want to draw, just for the sake of completeness, is I want to draw what the input signal looks like. We didn't explicitly show it on the other slide. So this class ends at 10:50, right? Not okay. Last time I went over, I forgot what. Okay, so this is 1 millisecond right here, this length. And this height is 1 volt. And so our input just simply looks like this. Okay. So now, moving on to the details of this. Warning you all, there are going to be a lot of steps in this problem, and I'm not even sure. I mean, it's 10:20 now. It's not a guarantee we're going to finish it before today is up, but we will do it right. Okay, so first step. We need to define some sort of circuit equation, KCL, KVL, etc., in order to describe its operation. So we're going to use KCL to describe the circuit's behavior. Okay. So we know that IN is going to be equal to IC plus IR. Right? That's just taken from applying KCL at that node right there. My goal here is to take what is a complicated problem, like all of our examples, and break it down to easy steps. So at least if you have problems going from A to Z, you never have a problem going from A to B, B to C, C to D, etc. Step number 2. So substitute for the currents. And I'm going to leave that open-ended because for the resistive elements, we're going to use Ohm's law, and for the capacitive element, we're going to use the differential expression that describes the VI relationship of a capacitor. Okay? And maybe I could write those real quickly. We know that for all resistors, V equals I times R. We know that for all capacitors, I equals C dVc dt. And I can write that in terms of current here. So I equals V divided by R. So we're going to take both of these and we're going to apply it to this KCL expression. And so what we're going to end up with is V in divided by R, what's called R1, is equal to, now let's look at IC. So IC, again, it's violating the passive sign convention. The current's flowing from the negative to the positive terminal. So instead of having CF dV out dt, I need to add a negative, right, to account for the fact that the current that we're looking at is flowing from the negative to the positive terminal. Then I'm going to do the same thing for the other. So VO over RF. So that describes our circuit. This, again, is I in, this is IC, and this is what we call IR. Okay, next. So we know we need to solve, and I forgot my D, sorry. I'll squeeze it in. Right, there's a derivative there, which I forgot. So we know we need to solve this first order differential equation. There's lots of different ways to solve it. We're going to go ahead and use Laplace. Okay, so for those of you who are not familiar, right, you should have a Laplace table that you are familiar with using. There's going to be one on the, there's going to be one on the cheat sheet. Let me find one here. There's tons of good ones online. I'll leave one up on the left-hand side of the screen, but you can see here the common Laplace transforms. Okay. So now this third step here, so we're going to apply the Laplace transform because it'll allow us to solve for the transient response, allow us to solve this first order differential equation. So how is that going to look? Let's talk about some of the Laplace transforms that we're going to use. So one is the Laplace transform of a value alpha, a constant, okay? That is the same as alpha times the Laplace transform of 1, right? Because this Laplace transform is a linear operator, which means that we can take terms that are added together and we can pull them apart, and we can pull out constant coefficients. So the Laplace transform of 1 is equal to that, 1 over s. So anytime we have a constant, we're going to end up with whatever the constant is divided by s. Then what about the Laplace transform of a function of time, but the derivative of it? Is everyone familiar with the prime notation for derivative, right? When I say f prime t, that's the same thing as the first derivative. So there's an entry for that in our Laplace table. I'll scroll down a little bit. Let's find it. And so what that gives us is s f of s minus whatever the initial condition of the function itself was. In many cases, we are going to assume that this is equal to 0. So these are the two that we need to use in order to transform what's above. So now let's do that. So first we find the Laplace transform of this. Laplace transform of that Let me go back to my slides here. Laplace transform of that is going to be, and actually I want to add one more thing here. I move it down. One last thing I want to add here is, what if we take the Laplace transform of just a function of time? That will just give us the corresponding function in the Laplace domain. For example, this right here, our v in, which I can call v in of t, and v out of t, that will give us the corresponding v in of s and v out of s. It's important to understand that. Okay. And if we have something multiplied by it, then it would just simply be pulled out. Okay, so now to apply the Laplace transform to the first element that's highlighted in yellow, what we'll end up with is 1 over R1 V in of S. Okay. Now, let's get the third term. I'll do that one next. So this is equal to negative 1 over RF VO of S. So this right here is the Laplace transform of V in of t over R1. This right here is the Laplace transform of negative V out of t divided by RF. Third term. For that one, we're going to need to apply that guy, right? We are taking the Laplace transform of the derivative of V out of t. So we're just going to follow the instructions that are provided to us. So it's going to be, and first thing I'm going to do is pull out any coefficients, because they'll go out front. So it'll be negative CF bless you, times, so S F of S. So that will be S VO of S minus the initial value of whatever the output voltage is. Close. And so this is the Laplace transform of negative CF, the derivative of VOT dt. We're going to assume that this goes away, and so we're left with a simplified version, which we'll show in a second. So if we group our terms together, what we're left with looks like this. So 1 over R1 VI of S equals negative 1 over RF minus CFS times V out of S. Right? Because the coefficients are this and then these two together. And so this is our transfer function in the Laplace domain. Okay. So now what we want to do we want to put it in the form of V out over V in, which is really not super difficult to do, right? Because we have pretty much everything we need. We'll have V out of S Sorry, I'm not doing this right. If I'm going to do this, this will go to the bottom. Right, these will cross. So actually what I'll end up with is this. We'll end up with 1 over R1, and then on the bottom I'll have negative 1 over RF minus CF times S. Okay. And I can't forget my, well, I'm going to go ahead and move this negative up top, and I'll make both of these positive. Okay. So, is this fine? Yeah, this is a fine form of the transfer function. Again, we normally don't want to have fractions in the denominator. So what we can do to get rid of that So to get rid of that, what we can do is multiply by RF over RF, right? Because what that'll do is get rid of that piece right there. And so for those of you who are really comfortable with this type of math, I apologize. But there's a lot of people in this class that are probably not so comfortable, or at least would really like to see it in this granular level. So feel free, if you really know this well, I won't be insulted if you zone out for a sec. But so let's continue this simplification. What we're going to end up with is negative RF divided by R1 over 1 plus RFCFS. Okay, good. So that's a nice looking transfer function for our analog integrator that we have so far. Next step. Okay. So, now to ask some questions. How the heck are we going to put this input here in the Laplace domain? Does anybody remember vague steps, strategies? How do we do this? So, does the unit step function sound familiar? Unit step function, right? We can take the Laplace transform of a unit step function. That's in our Laplace table, so that's no problem. So if we could take this pulse and we could decompose it down to a unit step function or more than one unit step function, then that would give us a path forward for moving into the Laplace domain, right? So next question. First off, what is a unit step function? Yes?
It's one at values greater than like t equals 0 and then 0 else.
Exactly. So it looks like this. Like you just said, right, it goes, and then it just goes on forever at 1. We can shift a unit step function right or left by putting t minus something. So this would be u, we usually call it u of t, right? That's what we use to represent unit step function. So this would be u of t. This would be u of t minus 1 millisecond, right? In that case, it would go to 1 millisecond, and then it would go on forever. We can also flip them upside down. So u minus u of t would look like this. Minus u of t minus 1 millisecond would look like this. So we have two different ways that we can play around with it, right? We can move it right or left, and we can flip it upside down, / make it bigger or smaller, right? We can provide a coefficient there. So, and the third thing that's important here is that for the Laplace transform, we can take the Laplace of things that are added together very easily. So, taking all that information, combining it, what would be a good way to try to represent this? Let's start off with a unit step function, u of t. That gets us all the way to right here. But now we need to go back down to 0. So if we subtracted a unit step function starting at this point, wouldn't that bring it back down to 0? Right? Because if you had something that went like this, then you had something that went like this, and you sum them together, the end result would be that. So that's what we're going to do. So to define our input in the Laplace domain, we're going to use unit step functions. We're going to have u of t, and then we're going to have negative u of t minus, and I'm just going to call it alpha. Okay? Now I'm going to actually write them in different colors. So u of t minus alpha. And you'll see the way that I did this problem is it's actually equally just as easy to do it for a generic pulse width as it is to do it for 1 millisecond. So I'm just going to make the pulse width beta. And we'll end up with an answer that will actually work for any pulse width. Okay, so now, I know we're almost done here. So this is a height alpha, this is 0, and this is a height negative alpha. And this right here is going to be our beta, and this is 0. Okay, so the red will look like this. Okay, the blue will look like this. And then the combo, so I'm just going to say the sum will look like and so to get our input, we're going to say that V in of t will be equal to alpha u of t minus alpha u of t minus beta. Where if we wanted to make it specific to the problem that we are doing, beta would be 1 millisecond and alpha would be equal to 1. And so I think, good morning everybody. So last time we had stopped off in the middle of this problem. What we're trying to do is calculate the transient response for a Miller inverting integrator op-amp with an input signal that looks like this. This 1 millisecond pulse with a height of 1 volt. And I don't have drawn here the full amplifier. This was the simplified version of the circuit that we derived by applying the ideal assumptions, which include the virtual short and the assumption that there's no bias current flowing into either one of the inputs. So we're not going to go through the whole beginning again because it's relatively long. What we are going to do is just very quickly breeze through the beginning steps and then jump back into where we hadn't completed stuff. Now, one thing I did add here that I think is important and we didn't necessarily talk about in the beginning was what are the basic steps in even doing this process? Because we sort of started without laying out a roadmap of how we wanted to finish. So how we do this is essentially this is the most important step. In order to determine what the transient response is, we need to take a convolution, which I'm sure is probably a dirty word to many of you from remembering how complex it is to do those in the time domain, to perform a convolution of the input signal and the transfer function. Okay. Now we could do that in the time domain. The math gets relatively sticky. But in the Laplace domain, it's a lot easier because convolution is simply just multiplying two signals together. So with the understanding that we have to do this, and we want to do it in the Laplace domain, what we'll do is first derive or convert our transfer function to the Laplace domain, and then take our input and also convert it to the Laplace domain, perform the convolution as a product, and then last, we'll take our output and go back to the time domain. Now, we completed this, we got to the very beginning of this, and we still have the rest of this to do. So very quickly, going through what we did, okay. We used KCL to describe our circuit's behavior, and then we converted that, or we made a first order differential equation out of that, right, which is shown under step 2. We then defined what were the Laplace transforms from the transform table that made sense to use. The most important ones were the most basic, which is what is the Laplace transform of any function in time, And then what's the Laplace transform of a derivative of that function in time? Again, we're going to keep using the principles of superposition. This is a linear operator, which means that we can apply additivity as well as homogeneity. We can pull out constant coefficients. We can also take the Laplace transform of additive elements separately. And so when we took our first order differential equation from the time domain down to the Laplace domain, we ended up with this. We did a little bit of algebra, combining some terms together and simplifying, and then we ended up with a transfer function that looked like this right here. We removed the fraction from the denominator, and we ended up with this. One thing I actually didn't point out was that we already had this answer. Actually, if you go to the lecture notes, the slide that presents the integrating op-amp with the parallel resistance, this was the frequency response. So anyway, next step. So now we're moving on to stage 2 of the problem, which has to do with the input, and this is where we left off. So we need to define the pulse input in the Laplace domain. And what we saw was, when we looked back at our Laplace table, there was no entry for that pulse specifically. Okay, which means we need to make one, or we need to cobble one together with different components. So the way that we did that was using the Heaviside function, or what we call the unit step function. And so we do know how to take the Laplace transform of a unit step. But first, before we do that, we need to create our pulse from those unit step functions. So here in the red, again, is the basic unit step function, where the height is simply multiplied by alpha. Then in the blue, what we did was we flipped it upside down, so the height is negative alpha. We also shifted it to the right by time of beta seconds. And then when we add the red and the blue together, we get the purple, which is a pulse that looks as we expect it to. So our input function in the time domain will be alpha u of t minus alpha u of t minus beta, where alpha is 1 and beta is 1 millisecond. However, for the purposes of this problem, we're just going to go ahead and leave it as alpha and beta. So what that does is it allows us to find a little bit more of a generalized solution for any pulse of any height of any length. Okay? So we'll get a closed form solution that won't work for any input, but it'll work for any pulse. So our height is alpha and our width is beta. So that's where we stopped. Now, converting this to the Laplace domain, so there's 3 Laplace transforms that we need to be familiar with. One is going to be the Laplace transform of a unit step function, which is equal to 1 over s. Next, how do we apply the time shift property of Laplace transforms? We know that the Laplace transform of f of t is equal to f of s. What about the Laplace transform of f of t shifted by beta? Okay, moving it right or left. Is that going to be f of s minus beta? I mean, as you can see, it doesn't work like that. F of t minus beta becomes e to the negative beta s f of s. So what happens is the time shift does not become a shift in the Laplace domain. It becomes this coefficient, this multiplier, e to the negative beta s, where the shift is denoted by the beta value. And so, if we were to take the Laplace transform of the second element here, Laplace transform of negative alpha u of t minus beta, we can pull out the negative alpha, that's going to be outside. We can take the Laplace transform of u of t, which is 1 of s, and then we have to make sure to include this time shift coefficient, which is going to be e to the negative beta s. So our answer, when we take the Laplace domain or convert this to the Laplace domain, is going to be alpha 1 over s minus alpha e to the negative beta s 1 over s, which is shown right here. So that was a lot of repeating the words s and alpha over and over again, but hopefully this makes sense. And if you need a little bit of catch up, right? Remember, this is all going to be in the lecture videos. Actually, the lecture video from last time is already posted, so you can go back and take a look at this, the beginning of this problem, and then, unfortunately, it spans 2 videos. You have to look at one and the other. But the end of last video and then the beginning of this video right now addresses the end. Okay, so let's continue on. So we've gotten through 2 steps. If we go back up here in our overview, so we're done with that. Now, perform the convolution in the Laplace domain, which very nicely is just going to be multiplying the 2 together. Now, we didn't explicitly give it that name, but right, I would call this here, that's the transfer function for our system that we're looking at. And then we've already said that this is our VI of S. So we have VI of S, and we have T of S right here. Okay, so let me see if I can copy this. That way I make sure not to copy anything wrong, because there's a lot of different variables and stuff. Okay, so that's the starting point. So this is a huge chunk of the, so the convolution's done. That step's actually really easy, because we just multiply. The hard part is this 4th step. So go back to the time domain. So we have our answer in the Laplace domain. That's our output. Going back to the time domain, does anybody remember what the strategy was for that? So you have this Laplace table, correct? And essentially, unless we're going to use the definition of a Laplace transform, which we're kind of assuming that we're not going to use, okay? Because again, that would be trying to apply the definition of Laplace transform in reverse to this would lead to some very, very messy math. So we, for better or for worse, want to use the Laplace transform table. The problem is there's only certain entries in the Laplace transform table, right? There's not one that fits this. So our goal, if you remember back to ELC251-06, is to try to break this down into pieces that look like elements from the Laplace transform table. And we don't need the entire thing to fit that form. We just need the individual added components to fit the form. So Let's say if we get one added element that fits this one, okay, good. We'll use that inverse Laplace transform. The second one fits another. We just need to work out so we can put everything into a bin and just apply the inverse Laplace transform. It's not a really easy process. The algebra can be a little bit funny, and also it requires some intuition, because what you have to do is you have to look at, the form that you have, and then you have to look at what forms are in the Laplace table and say, okay, what is my strategy? What forms am I going to be striving to achieve? So let's start off by doing that to give us a little bit of an idea of what might make sense. So I have a Laplace table loaded. And looking at our form the way we have it right now, we're at this top point here. So let me see if I can zoom this in. So we're currently up here. So it seems like our best strategy is going to be to try to get this into a form of something over S and potentially something over S minus alpha, right? Because we can break, and again, this is a little bit of intuition again, but we can break these pieces up into 1 over S times alpha times 1 over S times beta, right? We know that we can find the roots of the denominator and then split it up in that manner. I'm not going to go into too much detail right now because we're going to do all that. But all we really need is just a desired endpoint. We don't have to know exactly what it's going to look like at the end. So if we look at the table, we can see more or less we're going to be aiming for this entry as well as this entry right here. I mean, we don't have any cosines or sines. We don't have any repeated roots, at least not that we know of. So, I mean, really all it's doing is giving us a starting point. So we know that's sort of what we're striving for. And the good news is that you'll see there's several strategies that we're going to use over and over again. One of the main ones is going to be the partial fraction expansion. Does everybody remember what the partial fraction expansion is? So, picking up where I just left off a second ago before we had the technical issue, we need to make this fit elements from the Laplace table using partial fraction expansion. And this is going to be a common strategy we use over and over again. And we've kind of already seen what elements that's going to lead us to in the actual table. So let's talk about partial fraction expansion just for a second. There's two different ways to do it. There's a shortcut way and there's the formal way. I'm just going to talk about the shortcut of doing it. So let's say you have something that looks like this. So we have 1 over S minus alpha times S minus beta. Okay, and that is going to be equal to something called gamma over S minus alpha plus delta over S minus beta. Okay, so that's the form. How do we, the unknown is what is gamma and what is delta. What are the numerators of the two elements of the partial fraction expansion? And so what they are, gamma is going to be equal to, so first thing I'm going to do is I'm going to write out the original equation. Then what I'm going to say is, well, what is the root or the 0 of this term? What is the 0 of S minus alpha? Alpha, right? So what I'm going to do is I'm going to ignore that term. And then plug in alpha down here for the S. And what that leaves us with is that. So it's almost, one way of thinking about it is you almost like you cover it up with your hand, so you get rid of that part, and then you plug in the 0 that you're looking for, or the 0 associated with the coefficient you're looking for in here. So 1 over alpha minus beta, and that becomes what you're going to put right there. Okay, next, let's try the one for delta. So delta, we can just do it. We know that the 0 is going to be beta, and we're going to plug that now into this term. Whoops. We're going to plug that into this term right here. So what that'll leave us with is 1 over beta minus alpha. All right. So now there's an extended way of doing the partial fraction expansion. There are a couple caveats here with doing partial fraction expansion. If you have repeated roots or complex roots, then sometimes you can't use the shortcut. But honestly, for the example that we're currently working with, the shortcut works just fine. All right, so next step, step number 10. And I'm just going to say, because there's a whole bunch of steps in here, I'm going to say use partial fraction expansion plus just good old algebra to put VOS into the necessary form. That's really the best way to describe it, because it is an open-ended process. As we move forward, we'll start to see, okay, well, I need to separate out this term. This one is looking more like this entry from the Laplace table, etc. Okay, so we start off with V out of S is equal to negative alpha RF R1 RF CF, and I guess right off the bat, well, I'm going to leave the RF there for a second. I think I'm going to use it later. Although ideally, right, that goes away. So I'm going to pull out as many of the coefficients as possible times sorry, I'm looking at the wrong thing here. Okay, so if we look, trying to get both of them in one screen. So if we look at what we have just to verify the multiplication, right, we will have alpha times this, 1 over s times this. That'll give us negative alpha RF over R1, s plus s squared RFCF. So that's the combination of those two together. The next piece which there's a minus missing. No, the minuses cancel out. Right? So you have, so these minuses will cancel out, meaning the second term will be positive. So you'll have the same thing, alpha 1 over s times this. So that's the reason why you see this piece and this piece are exactly the same. But the second added component is multiplied by e to the negative beta s. So this is the transfer function with the two pieces separated out. Again, our goal is to divide and conquer. At least now we can analyze this separately from this one. Now we'll see that we don't have a form that fits this right here. Actually, we don't have to worry about this. Does anyone know why we don't have to worry about this? Well, it's not a constant. It has an s in it. But we know how to deal with this in the inverse Laplace transform. It's going to be a time shift. Okay? So this we don't have to get rid of. This will, essentially, these are going to give us the same function. This is going to be function f, whatever it is, and this is going to be that same function shifted by a beta. So it's almost like, even though we have two parts, it's almost like we're just trying to solve the same thing twice. Essentially, what we need to do is we need to get this into a form that fits the Laplace table, like I've said a million times. All right, so we're going to use partial fraction expansion right there. All right, and what I'm going to do is I'm going to address the pieces separately. So, because it's really, we're going to be doing the same partial fraction expansion 2 times. So what I'm going to do is I'm going to take this piece right here. All right, and we're going to call this, we'll just give it a name, g of s. Okay? And we're going to apply the partial fraction expansion to g of s. And then we can plug it back in, because really, right, g of s is also right here as well. Okay, so let's do the partial fraction expansion on g of s. So first things first, let's pull out all of the well, first things first, let's split it up into the two roots of the denominator. So we know this will be negative. The numerator stays unchanged. And actually it'll, well, no, we know what it is. It's going to be s times 1 plus s r f CF, right? However, we're more used to seeing the roots in the form, right? We want the form s minus something. So in order to do that, what we can do is multiply the numerator and the denominator by 1 over RFCF. Okay, and what will happen is then we'll get something which is more like the traditional form we are used to seeing, which will give us negative alpha RF R1 divided by RF CF over, and now this will become S times S plus 1 over RFCF. Right? Okay.
Professor,
Yep.
was there something you did to, I'm not sure if it's a mistake, but RF times R1 in the numerator?
Mm-hmm.
I think that should be, it should be divided by R1.
Oh, yeah, you're right. Yeah, that was a mistake. Thank you. Yeah. All right. So now we know what the zeros are. So the zeros will equal, obviously, 0 over here, right? Because when we plug in the 0. And then the 0 over here will be equal to negative 1 over RFCF. Okay. So now we So the takeaway from what we did up above is that our desired form is going to look like this. We don't know what is going to be in the numerator just yet, but that's the partial fraction expansion. Okay, so now we have g of s, again, is equal to, so I'm going to go ahead and pull out all the coefficients that are right here. So that gives us negative alpha RF over R1, RF, CF. And then our second piece now will be equal to and I just need to give it an unknown name. So what's the symbol I haven't used yet? I'll call it uppercase A over S plus uppercase B over S plus 1 over R F C F. Okay. All right, so maybe it would have been easier to split this up into multiple steps, but right now we're sort of taking it from this approach. So, so what is our A? And so I'd like for you guys to tell me that. So we're trying to apply a partial fraction. We've already pulled out the coefficient. So it's 1 over S times S plus RFCF. So our first 0 is S. So we're going to cover up this part. And then now we're going to plug in the 0, which means we're going to plug in a 0 right there. So it'll give us 1 over RFCF. Right? That's what happens when we apply our shortcut. Does that make sense? Yes? No? Again, we've taken this part away, so there's just a 1 left up here. Cover up the 0 we're working with, or the root that we're working with. We know the 0 of it is actually 0. So then we plug in a 0 right here. So we end up with 1 over 0 plus 1 over RFCF, which is the same as 1 over RFCF, which is RFCF. Okay. So now we get our B. So for our B, we go back up here. And remember, just for a second, we'll put a 1 up there because we removed all that stuff out anyway. So our 0 here is negative 1 over RFCF. So we're going to cover up this piece. Now we're going to plug in the 0, which is negative 1 over RFCF, which will give us 1 over a negative 1 over RFCF, which is equal to negative RFCF. It's a careful balance here. I'm trying to give detail without going super into detail. So hopefully it's enough that those who know it well will get something out of it. Those who don't know it well will give them at least a starting point to perhaps dig a little bit deeper. Because what we will end up with is 1 over okay. And then so in the end, what we end up with after the partial, so now our partial fraction expansion is complete. All right, and so what we end up with is G of S is equal to, we have to not forget about our little beginning part, so negative alpha RF over okay, and then now what we have is and this is good because you can see now we have added components that all fit with the forms that we see in the Laplace table, right? We have a form in the Laplace table that fits 1 over S, and we also have a form or an element in the Laplace table that fits 1 over S plus something. All right. So we've done a lot in this step. Step 11. So we are going to essentially clean up the math by inserting the results of the partial fraction expansion shown in what we were calling G of S into our VO of S. So we have, if you go all the way back up here, we have this as our output. Embedded within it is the G of S, 2 times actually. Then now we have this expanded form of g of s, and so we just have to plug it in 2 times and then split it up. So it's a lot, but at least it's in the right form, actually. So that's good. So why don't I copy this, and then we'll plug in what we need. Okay, so that's everything together in one place. You can see our original VO of S, and you can see we have our new G of S, and we got to plug that in there, and we also got to plug it in right here. And so the equation's going to get long. I'm not doubting that part of it, but we do have it in the form that we needed it in. Okay, so let's go ahead and expand this. Now the nice part is actually we can pull a lot of stuff out and make longer coefficients, which will shorten the fraction parts. So the first coefficient, or the coefficient for the whole thing, is going to be negative alpha RF over R1 RF CF. Okay, so that takes care of all of these. Then what we can do is from each one of those pull out another RF CF. So that'll make this RF squared CF, and I know that's a messy coefficient. We need to eliminate some terms, but I'm going to leave it the way it is just for right now. And so after we do that, then what we'll be left with is all ones in the numerators. So we'll have 1 over S plus a negative 1, because remember this is negative 1 RFCF. Negative 1 over S plus, and this is going to be 1 over RFCF. Now we have the exact same thing repeated, right? Because we have it here, and then now we have it here again. So again, we'll have 1 over S plus negative 1 S plus 1 over RFCF. The only difference is we can't forget that this term is multiplied by e to the negative beta s. And the one other thing we have to take into account is actually this was a negative and this was a positive, so the second term should be minus. All right. Okay, so now, we're almost done actually. So what inverse Laplace transforms are we going to use? I think we listed those out somewhere up above. Well, essentially, there's two different forms that we have. We have to deal with inverse Laplace transform of 1 over s, which is going to be equal to u of t, right? Then we also have to deal with inverse Laplace transform of 1 over s plus, well, I'll just go ahead and, well, I'll use an unknown. So I've used so many letters, I don't know what letters have been unused. We haven't used mu yet. Okay, so mu. And that gives us, if I look at the Laplace table, it gives us e to the negative mu t. Normally they use an a there, but we used an a somewhere, so I don't want to reuse it again. Okay, so that will address this term. That'll address this term. Now the remaining terms will be this combined with that, right? It'll be 1 over s times e to the negative bs, but that's easy because that's just the time shift. So now what's Laplace, inverse Laplace transform of 1 over s e to the negative b, or beta s? That's equal to u to the t minus beta. All right? And technically, actually, the definition of the Laplace transform, everything is, everything has a u of t that is multiplied by. That's just the definition. And so then the last one that we don't know is what is going to be the inverse Laplace transform of 1 over s plus mu when it's multiplied by e to the negative beta s. And so we'll just take this up here. It'll be e to the negative mu t. Anytime we see a t, we'll replace it with a t minus beta. So these four inverse Laplace transforms essentially these are all we need. So now we can go through and finish this. So VO of t. And I don't have room above, so I'm going to put it below. So VO of t is equal to, we'll pull out the coefficient by itself. Finally, I'll get rid of all these extra terms. So it'll be negative alpha RF So right, this will cancel out this will cancel out the squared, so we should just be left with negative alpha over R1. Oh, there's still one of the RFs left. Okay, now let's address that term that's highlighted. So what's the inverse Laplace transform of 1 over s? Ut. So what we have is u of t. Next, this one. We'll use this down here. So that will give us minus e to the negative 1 over RF CF t times u of t. So now we've gotten rid of that whole piece. Next, plus dot dot dot, but it's actually a minus. So minus, now we got to address this one, which is this times this, right? For that one, we'll use the third row that we came up with, which is going to be u of t minus beta. And then we have the final row, or the final element, which uses this one. So that will give us minus, and actually, you know, I'm going to write it using this form. This will be so much easier. exp just means e to the. So negative 1 over r f c f t minus beta u of t minus beta. And let me use that same form up here. exp negative 1 over r f c f t u of t. So that's it. It's a long road, and I know that you're thinking, can a computer do this, right? So, you know, as an engineer, it's really important to have a good mathematical background, and you know, there's not too many pieces. A lot of EC curricula, you know, ours included, have dropped out some of this stuff. There used to be a lot more of this type of stuff. But a couple pieces are still hanging around. I think it's important to understand it. So I know that this will take some time to digest. I'm hoping you should have a good background on it from ENG272. But this is something you will need to devote a little bit of time to. Okay, yes?
I'm still confused, like, on the final solution. You have this, but at the very beginning, the question was, what exactly is this actually?
Actually, I'm going to show you in a second. I'm going to graph it, and I'll show it to you. Yeah. Okay, so now switching back over to the slides. So another version of it, you can see how it's done. We end up with the same answer right here. So what is this? Okay, we take our op-amp, okay? It's a component, or we can call it a process, right? It has a given frequency response. We take our pulse, okay, which is 1 millisecond length and a height of 1, or in this case, we define them generally. So a height of alpha and a width of beta, okay? We take that pulse, we input it into the integrator op amp, and we get an output that looks like this. What we got when we didn't have the parallel resistor was something that looked like this. It simply ramped down and it leveled off. The version that we just spent like pretty close to an hour and 15 minutes working on was trying to get this same solution, but now with the parallel resistor. What we should expect to see is some leakage. Okay, first things first, now this will no longer stay constant because there is a path for the capacitor to discharge, and it will also apply some nonlinearity to the charging. So all I did was I took the function we came up with, which is here in the green, and I made a MATLAB script out of it. So from time equals 0 to 10 milliseconds, with a time step of, I guess, 10 microseconds, calculate our output, which is all this shown right here. I just put in what we had. And the answer looks like this. So you can see, first things first, it doesn't reach all the way down to the negative 10 as it did for the other solution, right? It only reaches about negative 9.6, and then now it doesn't keep the charge indefinitely. It discharges at a rate that's shown there.